For everyone's information, this webinar will be recorded. As long as you do not say anything, your name will not appear on the video. If you, however, speak out, ask a question or something, your name will appear in the recording. Okay, I think we can just start. Okay, welcome everyone. It's Friday again, and it's time for another webinar in this series of webinars for the Coastal Highway Route E39 project. Today we are lucky enough to have Yanyan Sha with us, and he will present on ship floating bridge collision analysis. So whenever you are ready, Yanyan Sha, you can begin. I'll just say that we'll allow Yanyan to present first, and then we can ask questions at the end. If you don't want to read out the question yourself, you can just type it in the instant message, and I will read out the question for you. Okay, Yanyan, please.
Okay, thank you, Matthias. Hello, everyone. Welcome to this webinar. My name is Yanyan Sha. I'm currently working at the Department of Marine Technology at Norwegian University of Science and Technology. In this project, I'm going to talk about our recent work in the past 4 years about the ship bridge collision analysis. This work is mainly done by me together with Professor Yogam Dao, also from NTNU, and Kato Durham from NPRA. So this is a brief outline of the work we have been doing. So first I'll briefly explain the project, which you may have already know, and then why we should design a ship collision, why it's so important. And following that, we will describe the works we have been doing, like how to design the floating bridges or floating tunnels against the ship collisions. So the work will be separated to several parts. So we'll start with discussing the current limits of the current code and guidelines, and then we will do some numerical analysis with ship collision with bridge substructures and superstructures. And then we have both local response of the structural components and the global bridge behavior. After that, we also did some work on the dynamic response of the floating bridges under the wind and wave loadings. And the last part is how we can assess the residual strength of the floating bridge after such ship collision accidents. So first is what is the project about? So we have the NPRA has started a project which intend to build a coastal highway from the South Kristiansand to the mid-Norway to Trondheim, where our university locates. So currently we have ferry crossings across several major fjords, but it's the ferry crossing are very slow and they have fixed schedules. So we intend to build some fixed installations, for example, the floating bridges or tunnels to replace the current ferry connections. So because the fjords are quite deep and wide, some of the fjords can have up to 600 meters depth, and the width can be 5 kilometers. So it's not possible to build fixed foundation bridges or tunnels due to the site limitations. So we have to find alternatives to build such kind of crossings. So we have the consultants have proposed several concepts to cross such kind of fjords. So we have different types of floating bridges, for example, the pontoon supported floating bridge, and also the tension leg platform supported. And we have also have floating tunnels which submerged under the sea surface, and we have combined floating tunnel and floating bridges. So there are many concepts. So the challenge is, except from the wind and wave loading, which is quite important for floating flexible structures, we also have ship collision challenges, because we have regular routes operating in the fjords. So there are many large container ships and also cruise ships passing by the installations. So they have possibility or for the ship collision accidents. So mainly we have separated the analysis into two scenarios. The first one is a ship collision with superstructures, where we have very high cruise ship or container ship which might impact against the bridge girder. And also we have a ship collision with bridge substructures. We have because we have floating pontoons or pylons around the sea surface, so there is a possibility that ship both may impact against these floating structures. So why it's so important? Here we show some figures of the past accidents which occurred in USA, China, and also recently in Japan. Can see both. We have two in the top left. Those are the accidents where the ship or barge hit the substructure, like the pier of the bridge, which lead to the collapse of the bridge. And the other four figures shows the ship collision with the bridge superstructure, where you can see the bottom right. Those two figures are showing the accident which happened quite recently, last year in October. The container ship was drifted by the tsunami and then hit the bridge, the connection bridge between the airport and the mainland. So you can see a large damage into the ship, and also the bridge deformation is quite large. So it's quite important to design the bridges against the ship collisions. So what's the challenge of design for floating bridges? For conventional bridges that you can see on the top left, these conventional bridges have fixed foundations to the seabed, so the global response will not be significant. So the critical thing is to design the local component of the bridges against the ship collision load. But the challenge for the floating structures is we both need to consider the local deformation, for example, the pontoons or the girders. We also have to evaluate the global movement or the forces in the whole bridge, because it's relatively flexible compared with the conventional fixed foundation bridges. And so in the design, we normally, in the current design code, they suggest to use a force to in the design process. But as I show in the bottom left, you can see the force can vary a lot due to the different types of ship, and also the impact location and the impact component of the ship. So a single load can not cover all the collision scenarios. Another thing is how the energy is distributed. So we not only need to consider about the energy which dissipated by the bridge, and also the energy dissipated by the ship, which may cause the human fatals, or in the ship, for example, in the cruise ship, there are many people on board. So this kind of damage we also need to evaluate. And the last thing is the response. As I said, we have to both evaluate the local damage to the bridge and the global response. So the approaches can be typically divided into like three aspects. So the first one is the most straightforward method, which we can conduct some collision tests or experiments. But the good thing is this kind of test is very direct, and you have a reliable result from the experiments. However, it is quite expensive, and it has a lot of limitations. For example, the site limitations, the time, and also the cost and equipment. So this kind of experiments haven't been done quite a lot during the past decades. So the most used method is use the static load, which is derived based on the test. So several widely used codes, for example, the Ashton code, which is used in USA, and also the Euro code, which is widely used in Europe. So they use the equivalent static load, which is calculated based on the displacement of the ship, the weight of the ship, and also the impact velocity. But this kind of the equation is quite simplified, so they can't account for the variations in the ship type and also the bridge structure, because if you have a concrete or a steel pontoon, the response will be totally different. And also it only accounts for the local impact load. The global response cannot be obtained through such kind of impact load analysis. And one major limitation is that these kind of code formulations are mainly focused on the substructure interactions, like the ship bow impact with the bridge foundation. But the ship impact with bridge pier, bridge girder is not well established. For example, Eurocode don't have such kind of suggestions for superstructure interaction, and Ashton only have introduced one coefficient to account for the superstructure based on the substructure force. So which is, you can see the figures on the right. So some of the code equations are overly conservative. So then we have the numerical simulation, which is most widely used in the current practice. So such kind of simulations are cost effective, and it can give reliable results if you have accurate modeling. And then the disadvantage of this such kind of analysis tools is numerical simulation needs a lot of time to develop many numerical models, and also the simulation time can be quite enormous. In past years, we have developed several numerical models, both the ship bows and ship deckhouse for superstructure and substructure analysis, and we have different FE models for the bridge components like the girders and the concrete and steel pontoons floaters. These are for the local analysis, and for global analysis we need to establish the whole bridge model. So we have simplified beam models for the whole bridges for different concepts. The last method is use simplified curves or analytical curves. These kind of curves are normally based on experiments or numerical simulations. These kind of equations are very easy to use for the design engineers. However, there are some assumptions behind these kind of equations, so these should be validated, and it may limit it to some certain scenarios. So the design basis for these kind of floating bridges for ship impact typically involve several scenarios. So we have characterized into bow collision with a pontoon and deckhouse collision with girder, which is superstructure. And we have both head-on, which is normal to the bridge, and also eccentric impact scenarios. And the bridge response should be evaluated both for during the impact and post-impact. During the impact, we need to evaluate the force, energy, and damage. And post-impact, we want to make sure the bridge will be safe under the following environmental loadings. So our work majorly in the numerical part, and based on the numerical simulation results, we also developed several analytical methods which can be used in the preliminary design phase. But for the experimental tests, we haven't have a lot of work in this because due to the cost or limitation, but we may find some resources to do it later because in the numerical model, it's quite important to make sure the numerical model are accurate. So we need some experiments to validate our numerical models. As you can see, one figure showing here, this is actually a indentation test for a steel panel. You can see the lines represent different groups of the work of different groups, and from the same test, the variation is quite big. The largest will be 1,000 kilonewton, the force, and the lowest is around 600-700. So the difference can be up to about 50%. So it's quite important to validate the numerical model with experiment tests, especially for the fracture modeling of the steels. And then for global analysis, we also established the numerical models and try to get the response of the bridge during the collision and after collision or under the environmental loadings. So we present several case studies we have done. So the first one is the regarding the concrete structure. So for example, the floating tunnel or the floating bridge where we have a concrete pontoon, then the ship passing by may hit the part of the pontoon. So then we develop a numerical model of the pontoon and also a cruise ship bow. And you can see the collision response. Generally, if we have a sufficient thickness of the pontoon wall, the pontoon will be able to resist the impact load from the ship bow. However, if we have a stronger ship, for example, the ice strengthened ship, or the pontoon wall thickness is reduced, there may be failure in the pontoon wall. You can see in this figure there is typically a punching shear failure in the pontoon, whereas a hole occurred in the pontoon when subject to a ice strengthened ship impact. So this numerical analysis. So we also developed some simplified method. This work is currently under review in one journal. So we, based on the numerical simulations, we see there are two typical type of failure mode in the pontoon, which is punching shear, like punch the hole in the pontoon, and also the fracture failure where the cracks may develop along certain yield lines. So based on these failure modes, we propose method to check both the punching shear and the fracture failure of the pontoon. And we propose several analytical equations which can be used in the design phase for fast estimation of the impact demand of the ship collision on concrete structures. And the second case is ship collision with floating pontoon, which is made of steel. So we have selected this curved bridge concept, and then the main pontoon, part of the main pontoon, as shown in the top left, we have modeled both the outer hull structure of the pontoon front and also the decks and stiffness in the pontoon. And the ship, design ship, in this case, we selected as a supply vessel. Bow, we have modeled, detail modeled the bow of the supply vessel, and then we conducted the collision simulation. As you can see, still for steel pontoons, it is not able to fully resist the impact from the ship bow. The ship bow typically penetrated into the pontoon. So there might be flooding risks in the pontoon in these kind of scenarios. So then we try to evaluate if we can locally strengthen this kind of pontoons with extra stiffness between the frames. So you can see we propose we can use 4 extra stiffness in the pontoon, which are most vulnerable to the ship impact. And you can see the response on the top right. So before strengthening, we have a large hole which was induced by the ship bob, and after strengthening, the damage in the pontoon is quite limited. So it's effective in reducing the damage to the pontoon. And if you can see the animation here, so after strengthening, the crushing mainly occurs in the ship bow and before it penetrates into the pontoon. However, we found that this kind of strengthening can have a negative effect to the connecting columns between the pontoon and the girder, because the force is transferred from the impact location to the column. So this part of the structure, the connection between the girder and the column and the pontoon, has to be checked if we strengthen it locally. One alternative is like we allow part of the pontoon to be crushed by the ship, but the floating condition should be checked so that the global stability of the bridge will not be compromised. Another case is for the superstructure analysis. So we have a floating bridge girder which has a concrete structure. So you can see we first analyzed if we have a ship bow which has a strong forecastle. So the forecastle may be hit with the side of the bridge girder. As you can see, the response, the damage mainly occurs in the ship bow, in the ship forecastle, but the concrete girder is generally intact. And most of energy are dissipated through the deformation in the ship forecastle, and the concrete girder would be have very limited damage. Further, we also investigate about the ship deckhouse, which is typically a deckhouse of a container ship, and we evaluate the impact with 2 locations. So one location is impact between the 2 decks of deckhouse, and the location 2 is the impact occurs where it directly impact with where the horizontal deck in the deckhouse locates. As you can see, the damage pattern will be different. So if we impact between 2 decks, so the girder will typically penetrate into the ship deckhouse. But if we hit in the deck level, then the crushing of the horizontal deck occurs, and the damage to the deckhouse actually increases. And this can be also be seen in the energy dissipation curves, where you see the red curve represents the damage, the energy in the location 2, and the black curve shows the damage, the energy in location 1. So this concludes the impact height, like the variation of the impact location can have a huge influence of the both of the energy dissipation and the structure formation. Following that, we also did with the steel girder, the ship deckhouse impact with steel bridge girders. So you can see this is a typical impact scenario where the container ship deckhouse hit with one of the steel girders, and the force level is around 20 to 30 megajoule. In this case, both almost all the energy goes to the ship deckhouse. The girder damage is quite limited in the initial phase, but later, when the deckhouse keep pushing, they also have damage in the bridge girder. And we also evaluate the effect of the girder shape. So we have to girder shapes. One is with the wedge shape, and one is trapezoidal prism shape. So we did the simulations for the two impact heights. One is between two horizontal decks in the ship deck house, and the location 2 is right at the horizontal deck. And you can see the force level will also be different. If we have a trapezoidal prism shaped girder, the force and energy will generally higher than the wedge shaped girder. And the impact location also matters. The black one shows location 1, like between two decks, and the red curve shows the force for location 2. So you can see the force and energy will be much larger in location 2 compared with in location 1. And we also plotted the code specified impact force in the figure. And you can see if the actual code generally has a good prediction, but then this is for the impact velocity of 10 meters per second. But if we vary it, then the force will drop significantly. And another design chart proposed by Patterson underestimate the force level. So, and we based on the deformation pattern of the structures in the ship deck house, we think if we can propose some sort of a simplified method which can be used by the engineers in the preliminary design phase. So we had a further look on the deformation mechanism of the structural components in the ship deck house. So we separated the deformation into 4 major components, like the front plating deformation and the stiffener which supports the front plating, and also the side panels in the deck house, and the last one is horizontal decks in the deck house. Then we proposed through a lot of numerical analytical derivations. We proposed the equations to calculate the force and energy in those components. For example, the front plating will be generally dominated by the membrane force and also the stiffness. For the side panels, we have folding in the beginning, and after that we have tearing failure after folding. For the horizontal deck, we have crashing failure and membrane failure. So use these kind of equations, we can, by summarize these kind of equations, we can have total force which occurs during a deck house and girder collision. So here we use this method. So we checked several impact scenarios. For example, location 1 is we hit right in the middle of between two decks, and location 2 is a little bit down, and location 3 is very close to the horizontal deck. And you can see the first row is the force comparison. We have the red curve from the analytical method and the black curve from the numerical simulation. And generally they match quite well. And also we compared with the energy dissipation in the bottom row. Still we have less than 20% error in our analytical method. This work has been published, but recently we have further extended this analytical method to account for the shape of the girder and also the location where we hit directly on a horizontal deck. And those I just talked are all about the local collision response. And then we also try to do some global response analysis. So based on the drawing, we also developed the full bridge model with beam elements, including the cable state parts and also the continuous pontoon supported part. Then we applied the collision by nonlinear elements. So you can see the top right figure where we have two springs connected to the bridge structure. So the spring 1 is the force crash depth curve, which we obtained in the local analysis, as we have shown before. And these kind of curves are used in the global analysis to represent the local deformation or the crash resistance of the ship and the bridge. And then the second spring is to make sure the ship will rebound from the bridge. And then we assign the mass of the ship to the node at the end of the spring, and then we give the initial velocity. It can be varied, so the node will move to the bridge, and the interaction between the ship and the bridge can be accounted for. And then we can done sort of a parametric study to vary the impact energy and the impact location, and we can check the whole bridge response on the ship collisions. Here we show an example, and the top left curve shows how the transverse and the displacement of the bridge distribute along the axis. So you can see the large displacement around transverse displacement around 2.5 meters will occur for a very large impact energy of 1,000 megajoule. And the other parts of the bridge generally have less response. We also can evaluate the force in any single element, for example, in the impacted girder or the cross beam or the columns, and in the stay cables. The bottom right figure shows the variation of the impact location. So if we have the same energy, if we hit close to the, for example, the north end, and then due to the constraint of the boundary which connected to the land, so the deformation will be less. But in this case, the force level in the bridge will be higher. And we can also do this for the superstructure analysis. For example, the deckhouse impact with bridge girder, and also the substructure where we have a ship bow impact with the floating pontoon. And you can see if we have a different impact scenario, the distribution of the energy between the local deformation and the global bridge motion can be very big. For example, if you see the right figure, where we have the same impact energy of 400 megajoule. If we have a head-on impact, the local energy will dissipate about half of the total energy. But if we hit sideways, the local deformation rise up to 77% of the total energy. So this means the local damage will be much larger than the head-on impact, but the global bridge motion will be reduced. So with such kind of a global analysis, we can have an overview how the bridge responds to the ship impact load. Here is a video. I don't know if you can see clearly. One is the cable stayed bridge, and another one is TLP bridge, where you can see the motion of the bridge, global motion of the bridge under the ship impact. And also we intend to evaluate the bridge condition before and after the ship impact. So in the first place, we did some wind and wave loadings on the bridge to see how the response, what is the response of the bridge, and then we can have a evaluation of the ship impact and reassess the bridge response under the same environmental loading conditions. So still we use the global model we have developed, and we have detailed modeling of the hydrodynamic properties of the floating pontoons. So we calculate the added mass and the potential damping of the floating pontoons. And also we calculate the wave loads, including the first order waves and second order waves Although the second load waves are quite small in the amplitude, but the frequency is quite close to the bridge natural frequency. So the second order waves are also considered, and also the wind load, which we consider both the mean velocity part and fluctuating part of the wind. So both the ship girders and the columns are considered for the wind load. Here are some results of the environmental loading. Basically, we can obtain all the information, including the displacement and the forces in the structural components. On the left, we show the typical transverse movement of one node and the force evolvement during the environmental loading. And on the right, we show how the total displacement or the acceleration and the x-axis moment distribute along the bridge. So you can clearly identify where the maximum response will occur and what is the amplitude. For example, in the middle figure, where we show the vertical acceleration, where you can clearly see two peaks which exceeds the limit of 0.5. So this kind of accelerations in these locations will be further evaluated. And then for the residual strength analysis, we first did the impact analysis in using local models. And then we have the different levels of damage due to the different impact scenarios. And then we can try to assess what is the residual strength of the bridge girder. So we take out the girder, we remove the ship, and then we fix the, we give the rotation or the moment to the bridge boundary. Then you can have sort of the weak axis, strong axis, and torsional capacity. So before impact, we can have an intact condition, and then we apply the rotation to the bridge girder. And after impact, we apply the same rotation. We compare what is the strength difference. So here you can see how it differs. So you can see before impact, which is in the intact state, we have a capacity around 900 meganewton meter. But then we have, with increase of the damage, like due to the increase of the impact energy, we have a larger damage in the bridge girder, and this corresponding to the reduction, further reduction of the weak axis moment. So for the extreme case, we have where we have around 200 megajoule damage energy in the bridge girder, then the reduction can be around 70%. So the residual capacity can reduce significantly. And here are some publications we have submitted and also published in the journals and conferences. And yes, that's all my presentations. Thank you.
Thank you so much for a very nice presentation, Yanyan.
Thank you.
I think that we will open up for questions, if anyone have. No one have any questions? Everything is perfectly clear. Well, I have to say, yeah.
Yeah, maybe I can ask a quick question. Yanyan?
Yes.
Thanks for the good presentation. I see that maybe I have forgotten, but in your whole presentation, you haven't mentioned the damping effect in all the analysis. Can you give some comments or about this, either in your structural analysis or the global analysis of the bridge global behavior?
Yes, thank you, Xu. For the local analysis, we didn't consider damping because it's basically a static analysis. So we have a prescribed motion of the ship and then impact in the structure components. So in which case damping or inertia doesn't have a significant effect on the response. Yeah. But for the global model, we include the hydrodynamic damping in the floating pontoons.
Yeah.
Yeah.
Okay.
Yeah.
And maybe one further question is that, for example, because this is quite fast, the ship collision happens very fast in a few seconds, right?
Yeah.
In this in your simulations, how the ADMAS and, for example, ADMAS terms are considered. Do you consider as a constant, or it's?
Yes. Actually, we use the constant because due to the software limitations.
Yeah.
So we intend to to compare the post and before impact condition, which we assume the numerical model is the same, and we correct the model the impact scenario, so we can evaluate the relative change in the response or the capacity of the bridge.
Yeah, but do you have kind of plan that you do kind of a sensitivity test on how this will influence the simulations or something like?
Yeah, we haven't considered that before, but this is a good suggestion. We can we can do some sensitivity analysis for this one. Yeah.
Yeah. Mm-hmm. Yeah. Okay. Thanks.
Thank you.
Thank you, Xu. We still have plenty of time for more questions, if anyone has. Okay. Well, in that case, I think I'll just take the opportunity to thank everyone for joining in on this webinar today. It's been a really interesting webinar from you, Yanyan. So thank you.
Yeah.
Thank you so much.
Yeah.
I'll also mention that the next webinar that we will have is on the 5th of April, and that will be Wei Wang, who will present on wave modeling in fjords. So everyone who's interested in that, please join again for another webinar on the Ether9 project, and then on wave modeling on the 5th of April. I'll now stop the recording.